Okay, here's my sample data. Red, orange, yellow, green, blue. The wavelength comes off of their data sheets. I didn't measure the wavelength, I just took it off the data sheet that came with the LED, and it's published online. All those wavelengths are times 10 to the negative 9 meters. The frequency, I just did F equals speed of light over wavelength, C equals lambda F basically. Here are my frequencies, times 10 to the 14th. These were the voltages that turned on each LED. Notice that they became progressively higher. Well, red and orange aren't that different, so red and orange aren't that different. But blue is way different than these other ones, so blue had a much different turn on voltage. And then, how do you calculate electron energy? Well, here's what happens inside the LED. Inside the LED, an electron crosses through a potential difference, whichever one these are, and the electron loses energy and shoots out a photon. So how do you figure out the amount of energy that an electron loses when it crosses through a potential difference? Simple. You do potential energy, or just energy, is charge times potential difference. Potential energy is charge times potential difference. So I take the charge of an electron, 1.6 times 10 to the negative 19, and I multiply by the potential difference. That's how much energy the electron gave up. Turned into a photon. Turned into a photon. Okay, so electron energy is electron charge times each voltage. Notice it's times 10 to the negative 19. So what am I going to do? I'm going to plot energy going up versus frequency going sideways. Here's what it looks like. Okay, so here are my dots. That looks like a pretty good line to me. That's a line that goes pretty close to the origin too. Isn't that nice? All right, so when I actually plot this, when I actually do a linear regression, I get a slope of 5.98 10 to the negative 34. Well, we know that photon energy is Planck's constant times frequency, E equals HF. Line that up with Y equals mx. Y is the energy, X is the frequency, then H is the slope. And so my slope was 5.98 10 to the negative 34. The real H, 6.63 times 10 to the negative 34. So, not terrible. Less than 10% error there. All right, so very good. The other thing I have students do is, you know you got to teach energy levels. Energy levels have shown up so much on the Physics 2 exams that have been released, but it's nice to learn it on paper. I would encourage you to actually have the students investigate real energy levels, and the energy levels I have my students investigate are those of hydrogen. So please teach the concept that electrons and individual atoms come in energy levels. Yeah, you're going to teach that. That's what is responsible for the emission and absorption of colors of photons for different gases. I use hydrogen as an example. Here's why. Because the energy levels of hydrogen follow the best pattern of all the elements. Each energy level is negative 13.6 divided by n squared. N is 1, 2, 3, 4, 5, and so forth. Okay, so here we go. Teach your students that visible light is only between 700 and 400 nanometers. I feel like that's something they do need to have memorized for the AP exam. So for this activity, for hydrogen energy levels, after I've taught about energy levels, and I've taught them the range of visible light, which probably happened way back in physical optics, honestly, but I'm going to go ahead and remind them of it now. Have students calculate the range of photon energies that we can see. What photon energy is the deepest red and the highest purple? What are those photon energies? How am I going to do that? Well, on the AP exam formula chart, we have E equals HF and C equals lambda F. Speed of light equals wavelength times frequency. You can actually solve for F in this equation and plug in, and you'll get E equals HC over lambda. Okay, so that's the equation. Not on the formula chart, but it's the combination of these two. E equals HC over lambda. But the formula chart tells us that H times C is yet another constant. Planck's constant, the constant speed of light, is 1240 in units of electron volts times nanometers. That's off the formula chart. Okay, so what am I going to do? For H times C, I'm going to plug in 1240, and I'm going to plug in that number of nanometers, and I'll get a number of electron volts. Plug in that number of nanometers, and I'll get a number of electron volts. Looks like this. Red is 1.77 electron volts. We can't see any lower energy photons. Purple is 3.10 electron volts. We can't see higher energy photons. Okay, so now the students know that this is the range of visible energies. Not visible wavelengths, not visible frequencies, but visible energies. Now I have the students calculate the energy levels of hydrogen from n equals 1 to n equals 5. Okay, so, and using this equation, negative 13.6 over n squared. So, for each of these n's, we plug in, we get a different energy level. Okay, those are different energy levels. So that's the next thing students have to calculate. And of course I make them actually draw the diagram with the lines, n equals 1, 2, 3, 4, 5. Okay, then I have the students complete this table. Okay, whoops, I guess the table wasn't there correctly. I'm sorry about this. The table starts with only these two columns there. So I'm going to stand here and like the students don't have these columns yet. Okay, so you have the n that the electron transitions from, and the n that the electron transitions to. Between n equals 1 and n equals 5, there are 10 different transitions. You can see all the possible transitions right here. So I asked the students, for each of these, what's the energy we're going from? What's the energy we're going to? So they're just copying that down. What's the photon energy, which is the difference? So all the students are doing is they're just copying over at n equals 2, that's the energy. At n equals 2, that's the energy. At n equals 1, that's the energy. So they're just going from this to this n. They fill in the energies, start and finishing energy of the electron, and they take the difference. And what I want them to notice is that these three transitions, of all of them, these are the three we can see. We can't see any of these other photons, but we can see these three. 3 to 2, 4 to 2, 5 to 2. Those are the ones that we can see. Okay, I'm getting students to that point. Now my question is, if these are the three we can see, what's their wavelength? What's their color? That's why I asked the students, what color am I about to see? Okay, so what do? They're going to use E equals hc over lambda again. They're just going to solve for lambda. And they get 656 for the low energy, 3 to 2, 486 nanometers for the 4 to 2, 434 nanometers for the 5 to 2. There's a table on the article, Visible Spectrum, on Wikipedia. Just show your kids this table or have them go there on their smart devices. And it has the wavelength range of each of the individual colors of the rainbow. So red is between like 700 and 630 or something like that. That's within the red range. This is really close to the border between blue and green. That's well within the purple. And then I say to the students, okay, now I'm going to show you real hydrogen. And I get a spectrum discharge tube and a hydrogen gas tube. I get the power supply, it's a big black box, and the hydrogen discharge tube, I borrow it from my chemistry people. And now they've done all this calculation, get to here, what do you see? And I'm going to give them either the rainbow peephole or diffraction glasses so that they can see the color coming out of the hydrogen. So let's see if the camera will pick up the color. Here we go.